So we know that we cannot estimate variance of sample mean if we have only one systematic sample. So we need more than one unless there is some preconditions which are satisfied, which means that they are all arranged in a completely random fashion, which uh, is not is often violated. So we need to have more than one systematic sampling if we want an unbiased estimate of variance of the sample mean. So how do we obtain more than one systematic sampling? So estimator of variance from more than one systematic sample. So we have total is n, and this is n times k. N is the total number of units, n is the sample size, and k is the every kth unit you are taking. Suppose n is divisible by an integer m. So n divided by m will be r, and n is going to be r times m. So we can replace that r times n here, and n will become r m k. Okay, so what is basically happening is that the sample size of n is getting further divided into m samples of r each. For example, if we have a sample of n of 100 and we had a sample size small n of 20 and a k was 5, so 100 is equal to 20 times 5. What if this 20 was further divided by an m of 4, 5, that gives an r of 4. Okay, so this sample size of 20 is being divided into 5 samples of 4 each. 5 samples of 4 each. But if you put all of this, we will still get 200 because r is 4, m is 5, and k is still 5, and that will give you 100. So how do we select more than one systematic sample using this process? What we do is we're going to select a number, one number between 1 and mk. So we are selecting, in this example, we are selecting one number between m is 5 and k is also 5. So we select one number that is between 1 and 25. We select one number so we select not one number, we select m, so we get this is 25, and we select m distinct numbers randomly from this. So m is, what is the m is 5, so we're going to select 5 distinct numbers, that will be 8, 3, 8, say randomly choosing these numbers. Now we need to get a sample size of r is equal to 4, and we're going to select the mkth unit, which is the 25th unit. So we add 25, so m and k we add to it. So that will be 3, then 28, then 53, then 78. Similarly, the next one will be 8, 33, 58, 83. Then we will have 12, 37, 62, 87. Then we will have 18, 43, 68, 93. Then 22, 47, 72, 97. Thus we have all of them have r is equal to 4, and there have 5 of them. So m is still 5, so we have selected 5. Still you can see that the total n is still 20. But instead of just selecting one sample of 20, choosing one random number and then taking 5, we have selected 5 systematic samples. So using some mathematical notations into this, we have selected m independent systematic samples of size r each. So y bar j, when j is equal to 1 to m, this, if m is 5, so it goes to 5, so there are 5 of those. We will stipulate, or we can show that the y bar j is unbiased estimator for population mean. Now we can also combine all these yj's to get y bar c. So what is y bar c? Y bar c is nothing but y bar c would be 1 upon m sigma j is equal to 1 to m y bar j. And this y bar c is also an unbiased estimator for y bar. Now what about variance? Variance of estimator y bar c. So that is going to be variance of y bar c, that is 1 upon m square sigma j is equal to 1 to m variance of y bar j. Why is that? Because y bar c is the average of y bar i's. So this is the natural expression y bar j. So y bar c is a average of y bar j's. So when you do their variances, they add, but the m will come out and it will be squared. So that is why variance of y bar c will be 1 upon m square variance of y bar j's. Now this is a situation where we can also estimate this variance, which will be v hat y bar c, by this formula 1 upon m minus 1 sigma j is equal to 1 to m, and instead of doing this variance here, we can also have y bar j minus y bar c. So this is nothing but sum of the squared deviation of overall sample mean from individual sample means. This is a sum of squared deviation of overall sample mean from individual sample means. So this gives a unbiased estimate of the variance of YC, but it is not very precise. So here's the simple law. If we believe that the order of units in the sampling frame is arbitrary with respect to the values of the target variable, then we can just do the systematic sample of size n. Then we can calculate variance of the sample mean. But if we cannot believe that the units in the sampling frame are completely arbitrary, then we need to take m independent sample and use the variance estimate from there. We have another example of this. So for example, we have n is equal to 40, k is equal to 10, and n is equal to 4. So from this we can choose this, that we can choose any. The k is 10, so 1 2 3 4 5 6 7 8 9 10 as any of these as an initial number we can choose, and then supposedly the yi's, once we choose them, we get a 4 sample size of 4 because n is equal to 4, and we get some random yi's, for example 0 6 8 26, based on whatever the first sample we have chosen. And for 2 we get 1 8 19 and 30, and similarly for this one we get 1 9 20 and 31, etc. And then you will have a y, because this is the situation where the population is known, we get the y. So because all these values are known for the whole population, we can calculate the mean y bar, which for example in this case comes out to be 18.2. We can also get the individual y bar, y for 1, which is for example comes out to be 12.5, y2 bar comes out to be 14.5, etc. So we can calculate it for all of them. Now we can also calculate the variance of the y bar systemic, that is going to be 1 by k, because we can take k times samples. I is equal to 1 to k minus y bar by ik minus y bar, and that comes out to be 111.63. Now obviously this is the true variance and not an estimated variance, and that is why what the variance means. We want to see the individual yi bars, how much they differ from the total y bar. But now if we draw a sample of size 4 from it, and by SRS WOR, what would happen? Now the population is known. We know that SRS WOR will give me a y bar which was going to be same as capital Y bar, which is going to be 18.2. Variance of y bar on the other hand is going to be s square upon n, 1 minus n upon n. Now S square is the population variance, which is going to be calculated by 1 minus and sum of basically all the values. I is equal to 1 to k and j is equal to 1 to n, yij minus y bar square. So you do all of that. So you do 1 upon 39 and you do 0 minus 18.2. You go all the way, square plus all of them. 18 point bar is the, and then you add them all up, and this will come out to be 136.25. So variance of y bar is going to be 136.25 upon 4, 1 minus 4 by 40, which is coming up to be 30.66. So you can see that the variance is coming out to be, by variance of y bar systemic is less than the variance of y bar by SRSWOR. So systematic sampling appears to be more precise. And why is that? One explanation for this is that if you can't see in this, but in this the trend was a linear and it seemed to be increasing. So population has a trend of linear trend, then systematic sampling is better. But there is another thing we had learned that is called the S square WSY, which is the within sample variance, which is calculated as 1 by k n minus 1, and then sigma I is equal to 1 k and sigma j is equal to 1 n. But here you will still have yij's, but instead of subtracting it from y bar, I'm subtracting it by yi square. So, and this you can calculate as 1 by 10 into 39, and then you will just add 0 minus 12.5 plus 6 minus 12.5, and so on. It will come out to be 162.62. So you can see that the S square is 136.2. We had calculated that here, while the S square WSY is 162.62. So what we are seeing is that the within sample variance is more than the population variance, or more heterogeneity within sample. There is more heterogeneity within sample, and in that situation systematic sample would be more precise than SRSWOR, when we have found with our expectation from the variance earlier also.